Welcome to Lecture 2.2, Initial Value Problems. As an introduction, recall that when we solve an ODE, we generally get an infinite family of solutions, and that's called the general solution. Once we specify a point, well, at least for a first-order differential equation, these are the only ones we've seen so far, once you specify a pair of an input and an output, in other words, what the function output is at a certain value, then we determine a particular solution from this infinite family. So as a definition, when we have an ODE, I guess I should say a first order ODE, with a specified point like this, that is called an initial value problem. And the solution to that is a particular solution to this initial value problem. As an example, let's revisit the equation that we solved last lecture. We solved the general solution, and now I'm turning this into an initial value problem by giving you an initial condition. So suppose Y is the temperature of a cup of water sitting inside a 72-degree room that initially is 90 degrees. So I'm not going to resolve this. I'm just going to write down what we got last time for the solution. Y of t is 72 plus c e to the minus k t. And now so we have this general solution subject to y of 0 equals 90. So let's plug in y of 0. So we solve these the same way. We plug in 0, or whatever this initial point is, and we set the equation equal to 90. Okay, so y of 0 equals 72 plus c, because it's c times e to the 0, and set that equal to 90, 90, and we get, solve for c, and we get c equals 18. And so that means our particular solution, y of 0, not y of 0, y of t is 72 plus 18 e to the minus k t. So this is a solution, and if we revisit that graph from the previous time, this is the solution that goes through the point 0, 90. So this point on the graph, it is this particular solution, y of t. And this is the point 0 in Cartesian coordinates, 0, 90. T equals 0 and y equals 90. So a lot of these initial value problems appear as word problems. And so here's an example word problem, and this one is exponential growth. And this actually comes from a real world example for me anyways. When I moved to Clemson in 2008, I was shopping for houses, and I found a house that I liked. It looked a little bit expensive. It was on sale for $319,000. This was in October of 2008, just after the crash. And looked up the records, and it seemed to be overpriced given the fact that the current owners had bought it for basically $180,000 5 years ago. And the question is, well, did it really grow that fast? Now, the growth rate wasn't constant, because again, if you think back to those times, the growth had gone up and then it went down after the crash. But one question I had, and I met with my realtor, and I said, this looks overpriced, and she did a little trick on the calculator and told me about what the average appreciation of value would be if it went from here to here. And I pulled out a piece of paper, no joke here, because I was teaching Math 208 at the same time, and I said, let me show you how to do this on paper, and it took me 20 seconds or so to do what I'm going to show you now. And I got pretty much the same answer as her, but it was a little more accurate. So first question, what is the average? So if this is the true value, then what was the average rate of appreciation? And the second part is, well, in actuality, the market had been increasing at a 9% rate over these years on average. It wasn't constant. So given that, how much is the house actually worth? So let's do the first one first. Part A is what's the average rate of appreciation? So we have a differential equation, p prime equals r times p, and we know that this has the solution. We solved this in the last lecture. P of t equals c e to the rt. Okay, so to make things easier, let's declare 2003 to be t equals 0, and let's call this to be t equals 5. So we're starting out at 2003, and our units of time, are years. So if this is the case, then we know that p of 0 is, again, here's our equation. So if we plug in 0, we just get c. So p of 0 is c times e to the 0, so that's c, and set that equal to, set that equal to 179,500. I should say one more thing up here. So because we're setting 2003 to be time equals 0, that means that p of 0 is 179,500, and p of 5 is 319,500. Okay, so this tells us right away that what c is. So now that we know c, we can say p of t equals 179,500. Okay, so this is one initial condition, and now we have a piece of information we have not used, and let's think about what that's going to be used for. So we know what c is, but we actually don't know what r is. So when we use this piece of information like we did this, when we're going to plug in t equals 5, set the resulting thing to 319,500, and we're going to use that to solve for r. Oh, let me finish my sentence here. I forgot about this. E to the rt, of course. Yeah, so we're going to plug in t equals 5 into here, set that whole thing equal to 319,500, and solve for r. So let's do that. So we're going to solve for r. Remember, that's the rate that we're looking for. So p of 5 is, so we plug in 5, we get 179,500 e to the 5r, and set that whole thing equal to 319,500. So now, somehow we have an equation, solve for r. This is something, it may look daunting, but it's just something we can do with logarithms. So, solve for r in that equation. The first thing we should do is, so we're going to divide both sides by 179,500, and then take the log of both sides. So we get e to the 5r equals 319,500 over 179,500, and right away I'm gonna get rid of these zeros because they cancel. So let's take the log of both sides, the natural log, but we usually just call that log. So the natural log of e to the 5r equals the natural log of 3195 over 1795. And if you use a calculator to do this, this is approximately, well, actually, I don't need to do that just yet. Yeah, I'll get rid of, well, I guess I can probably erase that. Yeah, let's erase that. So now that the natural log and the e cancel, so this tells us that, let's move down, well, I can fit there, I think. This tells us that 5r equals natural log of 3195 over 1795, and now we can easily solve for r, and we get r equals 1/5 3195 over 1795, and if you plug this into a computer, you get approximately 0.115. So our rate was a 11.5% rate. So that means that if the house really was worth this much, then it was increasing on average at an 11.5% rate per year. And I knew sitting in my realtor's office that that was not the case, that in fact the market had been increasing at about a 9% rate. So I took out a sheet of paper. This is something that my realtor did not know how to do using her little calculator trick, and quickly computed how much the house should be worth. So let's do that. So part B is assuming that the market had increased at 9% per year on average, how much is the house worth? Well, in that case, that means R is 9/100ths. And so how much is the house worth? Well, this is in 2008, so what we really want to do is compute P of 5. So that is 179,500 times e to the r times t. So e to the 9/100ths times t. And so that's 45 over 100. And if you compute that out, this is approximately $281.512. So I think what I did is I told the realtor I want to put in an offer at $280, and with justification why. And the next day, this is no joke here, they took it off the market. I don't know if they were intimidated or they realized that how badly they overpriced their house, but they realized they weren't going to get anything close to this. And the next day, they decided to not sell it anymore. Okay, so one more example. This one is exponential decay, again, but not to it's exponential decay to 0. This is a classic problem in differential equations. There's a decent chance this will appear in one of your exams. It does all the time. So now you have 10 grams of a radioactive substance, and 3 years later you have 4 grams. So one question is, what's the half-life? And I mean, in other words, how long does it take for 10 grams to get down to 5, or n grams to get down to n over 2 grams? And then once we have that, tell me how long until only 1 gram remains. So this is an initial value problem. Let's write down the initial value problem first of all. This is the initial, so where m prime, so m of course is the mass at time t. So m prime equals negative km. That's our differential equation. We have an initial value. Let's declare that we have 10 grams. Let's do that let's call that at time equals 0. So let's say m of 0 equals 10. We don't have to. I mean, we could say that time equals 0 would be 4 grams, but trust me, that's harder. Because then you have to go backwards in time and deal with negative numbers and logs of negative numbers, which become positive, but there's so many ways to mess that up. So let's put our initial value down. This is m of 0. Well, that's supposed to be a 0. Let's see if I can fix that. Redo it. M of 0 equals 0. But let me add one more condition. We also know that at 3 years later we have 4 grams. That means m of 3 equals 4. So let's write down that condition as well. Call this an initial condition even though it's technically not at time equals 0. And you may be wondering, why do we have 2 initial conditions? Right? Well, the short answer is because not only do we not know the constant of integration that will appear, but we also don't know what this k is. And the general rule of thumb is every time we have an unknown parameter or constant, whether it be k or whether it be c, we need a condition like this to determine what it is. So the general solution is m of t equals 10 e to the minus kt. You don't have to read this every time. It's perfectly fine. In fact, encouraged for you to have you memorize it. So for part A, the half-life, remember what is the half-life? It's the amount of time until half, in this case, 5 grams remain. So how do we determine that? Well, let's write out our equation, 10 e to the minus kt, and let's set that equal to 5 and solve for t. So solve for t. So if we do that, we have e to the minus kt equals 5 over 10, or 1/2. Notice that it doesn't matter how much we start with, whether we start with 10 or a million. The half-life is independent of our initial amount. So here's what we have. Let's take the natural log of both sides. I like to write this as natural log of this whole equation. So by this I just mean take the natural log of the left-hand side and equate it to the natural log of the right-hand side. So the natural log of e to the negative kt is negative kt, and set that equal to I was a step ahead of myself. Set that equal to the natural log of 1/2. But what I like to do is, I don't like natural logs of fractions that are smaller than 1. I like to say this is negative natural log of 2. You don't have to do it, but it's just a convention that I like, because I don't like fractions. So solve for t. So solve for t in this, and well, we set that equal to that and solve for t, and we get that t equals 1 over k times natural log of 2. And that is the half-life, and it only depends on k. Okay, so we've solved for that. We found the half-life. So we still need to figure out what k is. Yeah, we have the half-life in terms of k, but we don't know what k is. And this guy here will help us get k. So to solve for k, so let's find this. So we will find this next, and we typically do the same method. We take one of our unused conditions, plug in the input 3, set it equal to the output, and that's what we get. So solve for k. So we have m of 3 is 10 e to the negative 3k, and set that equal to 4. Solve for k. So we get that e to the minus 3k equals 4/10. I'll write that as 4/10. Take the natural log of both sides. This time I'll do it in our head, and we get that negative 3k equals the natural log of 4/10, which is 2/5, the natural log of 2/5. And again, I like to make that I like to make that number greater than 1, so this is negative natural log of 5 halves. Because in general, I like the fact that our constants, r or k, are positive. So in this case, we are going to get, let's see, so we have that, so we got to solve for k. Let me circle this, solve for k. And if we do that, we get, what is k here? K is 1/3 natural log of 5 halves. Okay? So the half-life, now I'm running out of room. So let me put up some space here. So the half-life, well, we already found the half-life. It's half-life is this here, but now we actually know what we know the half-life and we know what k is. So the half-life is let's see, what was it? It was 1/k times natural log of 2, and again we know what our k is, so if we plug k into that, we get 1/1/3 natural log of 5 halves times natural log of 2, and this thing simplifies as 3 natural log of 2 over natural log of 5 halves. And that is our half-life numerically. That's exactly, not in terms of k, actually in terms of numbers. Okay, and also the general solution, here's our general solution, now we know what k is. K in our general solution, where was it? It was, it was here somewhere. That's right, it was down here. So this particular k, if you want to, you can plug this thing into here. But personally, even when I figure out what k is, I like to leave it in terms of k with a note like this on the side, because it's so much messier to have 1/3 natural log of 5 halves in all your equations rather than just k and knowing what k is. Okay, so let's do the second part. How long until only 1 gram? So I'm going to take my advice that I just told you, and I'm going to write, even though we know what k is, I'm going to write m of t equals 10 e to the negative kt. And yeah, I'll put on the side what k is. K is 1/3 natural log of 5 halves. So how long until 1 gram remains? Well, how do we do this? This is an equation for the mass at any time t. So we want to know when the mass is equal to 1, what's the time? So solve for t. Now sometimes it may be, one advantage of putting in the numerical k in here is you know what you have to solve for. It's the only variable that's left. But if you understand what's going on, I think it's actually easier to, I prefer to keep the k there, knowing that I know it, and just don't have to write it. So let's solve for t. So again, we are solving for t in this equation. So again, before we take the natural log of both sides, we need to make this monic, divide by 10. So we get e to the minus kt equals 1/10. Now we compute the natural log of this equation. That's my notation for that. And we get that negative kt equals natural log of 1/10, which I like to write as negative natural log of 10. Doesn't that look so much nicer? And now, what are we solving for? Remember, we are solving for t in this equation. So that tells us that t equals negative natural log of 10 over negative k, or just, if you prefer, t equals natural log of 10 over k, or if you really want, you can write this as 3 natural log of 10 over natural log of 5 halves, because we actually know what our k is. Okay, and that is that. So last example, word problem. Again, these initial value problems, as you've seen, they frequently come up in the form of word problems. I mean, I don't have to give you a story behind it, but it's kind of cute to do it, so why not? And here's one that doesn't work as well for an online course, but it works well for an in-class course, because being from Seattle, I frequently come into class with a cup of coffee. So let's suppose that my coffee is 120 degrees when class starts, and the classroom is 75 degrees. And after 30 minutes, the coffee has cooled to 100 degrees. So first question, what will the temperature be at the end of class? That's T equals 50. And let's suppose that it was brewed at 160 degrees. When did I brew it? So to do this, the first thing to do is to write down the differential equation. This is something that you should know by now. So T prime of T equals K times 75 minus T of T. I guess I don't need to write the of T's by now. And so it's always good to write down the initial conditions, and before you start, write down all the information you know. So class starts. That's going to be easier to say that's going to be T equals 0. So when class starts, the temperature is 120, which means T of 0 is 120. And after 30 minutes, that's going to be, let's use minutes. You could use hours and say T equals 1/2. But again, I told you I don't like fractions. So after 30 minutes, the coffee is 100 degrees. So that means that T, let's use black again, T of 30 equals 100 degrees. So what will the temperature be at the end of class? Well, we need to solve this equation, and you don't have to do it from scratch. You're welcome to have learned this one because it's one of our fundamental equations. The solution is T, big T of little t, is 75 plus C e to the minus k t. And again, we have two unknowns. We have C and K, so we have two conditions that will help us determine those unknowns. Okay, so we have to plug in these conditions. A great rule of thumb is to do the easiest one first. And this one's going to be easier because it's got the most zeros. So T equals, let's plug in T of 0. Well, that's 75 plus C, and set that equal to 120. And now we see that our constant C is equal to 45. And remember that that is our initial temperature difference deviation from the room temperature. It's 120 is 45 degrees above 75. Okay, so this constant was this condition was a success if it got us what we needed. Now let's use this one. So you define K. So let's T of 30 is 75. So let's plug in 30. So we're plugging in 30 into here. And we know what C is. C is 45. So 75 plus 45, e to the minus 30k. And at time equals 30, the temperature is 100. So now we have to solve for k. Okay, so solve for k. Let's subtract 75 from 100, that's 25. Divide by 45, that's 25 over 45. So I'm going to do that so I'm going to write this as e to the minus 30, okay, equals, what did I say? It was 25, not 24, 25. 25 over 45, which, what does that simplify to? That's 5/9. All right, so let's take the natural log of both sides of this, and that tells us that negative 30k equals the natural log of, this is 5/9, so the natural log of 5/9. And again, I like to write this as negative natural log of something that's greater than 1. And now we can solve for k. So now we have that k equals 1/30th times natural log of 9/5. And again, one advantage of my convention is if I always pull out those negative signs, right away I'm guaranteed that this is a positive number. If I were to have natural log of 5/9 in there, that would secretly be a negative number, and I have a negative sign out here, so I have a double negative. So right away we can see this is a positive number because there is no negative sign out in front. Okay, so the temperature, well, let's see, back to our question. The temperature at the end of class is, well, we take our solution and we plug in 50. So the temperature at the end of class, temperature at end of class, so this is the answer to part A. I should probably put that. Temperature at the end of class is just none other than T of 50, which is 75 plus 45 e to the minus 50 times k. And again, I am not plugging in my actual value of k. This, I'm just going to leave it like that. And on exams, you are welcome to do something, as long as you tell me what k is and you have the correct function like this, you're good. Okay, let's do part B. Suppose it was brewed at 160 degrees. When did I brew it? So let's think for a moment. T equals, when class starts, this was T equals 0. And if we're going to plot what this looks like, what the solution looks like, let's do this for a moment. So say this is 75, and so 120 is up here, and so temperature of the cup of coffee looks like this. This is big T, and the temperature was brewed at 160. So that means that 160 is up here, and I'm asking what time, when did that happen? That's supposed to be at 160. In other words, what time is this? TB for time it was brewed. Now, notice this is going to have to be a negative number because it's before class starts. So this is a good thing to keep in mind, because if at the end of the day your answer is positive, you did something wrong, and you should check this. And I've seen dozens and dozens of, probably hundreds of homework assignments where someone gets a positive answer for something that's clearly negative, and this doesn't cause a red flag. You know, it's really, you probably dropped a negative sign, and you're going to lose points if you don't go back and catch it. So be aware of that. In advance, whether your number should be whether your answer should be positive or negative. Okay, so how do we do this? Well, let me rewrite the solution that we have so far. Our particular solution, again, this is our particular solution satisfying these initial conditions. That is, let me use the pen. 75 plus 45 e to the minus kt, and I'm going to put k up here. K was 1/30th natural log of 45 over 25. But I'm going to keep it as k. So we want to know, when was the temperature equal to 160? In other words, solve for t. So let's do that. So let's subtract 75 over here. What does that give us? That's 85. Divide by 45, and we get e to the minus kt equals 85 over 45, which, what is that? That's 17 over 9. So let's take the natural log of both sides, or I guess of all of these parts. Natural log of maybe I didn't need to write down this details, but natural log of 17 over 9. So we have that. We get that negative kt equals natural log of 17 over 9, and we get that t equals negative 1 over k times natural log of 17 over 9. And if you prefer, you don't have to, but if you want to, you can put this k back in here. And if you do that, dividing by that k, what does that give us? That gives us, divide by 1/30th, that gives us a negative 30 natural log of 17 over 9, and over natural log of 9/5, because, yeah, that is 9/5. And notice this, because these numbers are greater than 1, both of the natural logs are positive, and so this number, this time, is negative, and that is indeed, that checks out. If we had gotten a positive number, we would be careful. And this is, again, why if I had left this as natural log of 5/9, then the negative sign would not be there. And I've seen students do that and say, well, I must have made a mistake because my answer is positive. Well, it's not positive if you take the natural log of something less than 1, like natural log of 5/9. Okay, so that is, again, this is a very, very standard type of test question, something like this.